Previous class we solved KCL here, how to apply KCL in that circuit. Now we apply KVL in for loop, loop 1, loop 2, loop 3 or loop 4. Okay, so you now the name the loop that's called loop 1, name is loop 2, that the loop 3 and loop 4. Okay, there is a for loop. Okay, and apply KVL in for loops. First loop 1, and you know the KVL. What is KVL? Algebraic sum of all potential drop in a closed loop equal to 0. So here I will choose the direction. My direction is suppose clockwise direction. In loop 1 apply KVL in clockwise, starting from point here. So see that minus to plus, that is a plus, minus, minus V1, and potential drop across these resistor. Suppose the resistor called R1. Okay, so resistor R1, so potential drop R1 is IR1 and the same direction, so that is a plus, same direction with a plus, opposite direction. If I satisfied that the black color direction or the green direction satisfied, then plus, otherwise the minus. So that is I1 R1. So here V2 plus to minus, plus V2, and here in this resistance called suppose R2. So in that direction, that's why these are the same direction, plus I1 plus I3 plus I4 times R2. So potential drop across R2, that is equal to 0. That's the KVL equation of loop 1. Now loop 2, same clockwise direction we choose. Okay, in loop 2, so from starting from here, so potential drop across, suppose this resistance is R3, potential drop across R3 is I1 plus I2 times R3 in the same direction, will be the plus. So I1 plus I2 times R3, and that's the R4, suppose this resistance is R4, and that's the same direction of, so same I1 plus I2 times R4, so potential drop across R4. Now this resistance, suppose this resistance name is R5, so same. Okay, so plus in that direction obviously, so choose plus same direction, I1 plus I2 plus I4 times R5, and here current across in that internal these two terminal from plus to minus direction, that's the opposite direction. Our direction is opposite direction, so that's why with a minus to plus, so minus V2 equal to 0. That's the KVL equation on loop 2. Now apply KVL equation on loop 3. Similarly clockwise we choose. Okay, clockwise direction. So now loop 3, from starting from this junction J2, plus to minus V3, same direction, and this is called R6. Suppose the resistance R6, and current passes through that I3, I4. So the same direction, sorry, opposite direction. That's the opposite direction. Okay, so that's why minus I3 plus I4 times R6. So that is bottom to top, that's a top to bottom, that's a negative direction. and now these resistors R2. So that's the obviously minus direction. Minus I1 plus I3 plus I4 times R2. 1, 2, 3. Okay, 1, 2, 3. That is equal to 0. So apply KVL in loop 3 and final loop 4. Here we choose same clockwise starting from here V4. So suppose that is a R7 given name V4 plus to minus obviously plus V4. That direction is the opposite direction. We choose right to left, but current direction in I7 is R7 is I4 left to right, to opposite direction. So potential drop across R2, that is equal to minus opposite direction I4 R7. So that is in opposite direction minus V3 minus to plus same. So R5, they are obviously opposite direction because the clockwise direction, that's the anti-clockwise direction. So minus potential drop across R5, the current passes through from Ohm's law, I1 plus I2 plus I4 times R5. Final gets 0. So 1, 2, 3, 4, that is the count 1, 2, 3, 4. Okay, clear? That's the KVL equation number 4. Sorry, 1, 2, 3, 4. That's a basic way to apply KVL equation. Okay, and we solve 10 to 15 numericals in the lecture series. We solve a maximum type of numerical here. Okay, solve this. So if you try practice how to apply the KCL KVL in numerical example here in NCERT book, Newton's book, or any other book. Okay, practice very important. Okay, now clear how to apply KCL KVL in a circuit. Another important is a Wheatstone bridge. In our syllabus, Stone bridge is a special type of circuit. Okay, a circuit is look like this. As there is a resistor here and a resistor here. There is another resistor here. There is a source. Okay, and a galvanometer connected from here. So the given the name of the resistance is suppose R1, R2, R2, R3, R4. Okay, there's a battery, the positive terminal, negative terminal. So current direction. Okay. There's a I current here, that is called I1. Apply KCL here. So I1 and I enter, I1 leave. So that is X. So X equal to enter with a plus. So say that enter plus, either enter minus, but both are same. The I choose I enter with the plus, leave the minus, X equal to 0. So I minus I1 equal to X. So you get I minus I1. Okay, there is a galvanometer current, suppose called IG. Okay, so I1 enter, IG leave, so that's current passes through the R3 resistor, that is equal to I1 minus IG. Okay, similar the current passes through the R4 resistor, I minus I1 enter, IG also enter, so I minus I1 plus IG, and here both are entered. Okay, so enter with the plus, leave the minus. So suppose if I say that is a y, so enter I1 minus IG, and from here also enter plus I minus I1 plus IG. Obviously leave with a minus, y equal to 0, 0 cancel, I1 cancel, so y equal to I. To satisfy our KCL equation. Okay, let's see that. That's the I current here. Okay. Okay. There's a apply KCL and directed current direction and value of current we find here. Okay. Is that part. Now, in balanced condition, Houston Bridge, in balanced condition, galvanometer current equal to 0. Okay, as a condition here, very important as a balanced condition. Now we apply KVL. KVL in suppose in that loop 1. Okay, so KVL in loop 1. So potential drop, you see that is R2, that is I1 R2 at the same direction. So I1 R2 plus IG. Okay, so here IG, and suppose the potential drop is called VG. Okay, so ignore that actually. Okay, RG, IG plus RG. So actually IG be the 0, so ignore that part. Okay, so 0 current refer as a open circuit. Okay, so that means the voltage VG be the 0. So here in that potential drop across here, suppose that is the opposite direction minus in that. So I minus I1 times R1 equal to 0. So I1 R2 minus I R1 plus I1 R1 equal to 0. So I1 equal to R2 plus R1, that is equal to minus plus I R1. This goes here. So I1 by I we get R1 by R1 plus R2. That's the equation number 1. Now another loop. So here in that loop we apply KVL in that loop. Loop 2. In loop we apply KVL. Loop 2. In loop 2, now starting from here, I1 minus IG in the same direction, potential drop across R3, I1 minus IG times R3, same direction. Similar here, that's the opposite direction, minus I minus I1 plus IG times R4, potential drop across R4. So that is shortest path, that is equal to 0. That's the equation number. Not put a equation number here. Now solve this. So Ig be the 0 in balanced condition. So Ig 0, Ig 0. So I1 R3 minus I R4 minus minus plus I1 R4 equal to 0. So I1 common, R3 plus R4, here this minus goes to right side, plus I R4. So I1 by I we get R4 by R3 plus R4. That's the equation number 2. And you see that 1 and 2 are equal. So 1 I1 by I1 by I, that's obviously 1 equal to 2. Now get R1 by R1 plus R2, R4 by R3 plus R4. Now reciprocal both sides. R1 plus R2 by R1, R4, sorry, R3 plus R4 by R4, separate R1 by R1, R2 by R1, R3 by R4, R4 by R4, cancel these two, cancel these two. That is a 1, that is also 1. 1 obviously cancel. The final answer we get, so R2 by R1, that is equal to R3 by R4. That's the balance condition of the Wheatstone bridge. Okay, that's a balance condition of Wheatstone bridge. Okay, clear? There's a basic circuit. Wheatstone bridge, a basic circuit is given here. Now apply KCL KVL and get a some balance condition. Okay. Similar that, another important concept is a meter bridge. Similar like Wheatstone bridge. Meter, a application of Wheatstone bridge. There is a 1 meter rule. This rule is 1 meter. Okay, and rule here. So now connection like this. Much thicker than. So connection register here, another register here. Okay, that's a 1 meter rule, means 100 centimeter. The length of the rule. Now a battery connected here. Okay, suppose that is called R1, that is called R2. There is a jockey. There is a jockey connected any point. Okay, suppose jockey connected here. Connected here, and the length is now say that this length is L1 or called L. So there is a length L, and this length is 100 minus L. Now here we apply Wheatstone bridge concept here. So R2 by R1 means this by this, that is R3 by R4. Now we apply at R1 by L, and L is directly proportional to R. We know that is R equal to rho L by A. So R is directly proportional to L. So means more length means more resistance, less length means less resistance, means more length more resistance, less length less resistance. Okay, the length of conductor means the length of length of rule, 1 meter rule or 100 centimeter. So now that R1 by L, and that is equal to R2 by 100 minus L, and that is equal to R1 by R2, and you get L by 100 minus L. Okay, that's the easy concept here. And R1 equal to R2 times L by 100 minus L, and box that. The application of Wheatstone bridge. That's the mainly application of Wheatstone Bridge. Very easy concept here. Okay, so we complete our syllabus in third chapter, but so main important is that solving that numerical. Okay, very important. Yeah, you get a 2-3 numerical in each and every year in CBSE, ICSE, or ISC, any state board exam. You get NEET or JEE exam. You get 2-3 numerical in each and every year. So that's why that solving numerical is very important. Without solving numerical concept, I think there's too much confusion. Okay, solving numerical, that's the easiest way to remember the each and every concept. So next class we solving some numerical. Okay, these are KCL KVL application or basic some numerical other in this chapter other topics. Okay, if you have any doubt, always put in comment section. I will try to give the answer. So today in the class here. Thank you.